I'm super excited about this lecture. This is the start of one of my absolute favorite topics of all time, and that's transaction processing. So hopefully you guys, and it's funny because what, it's like week 7? Is that right? Week 8? I can't remember anymore.
They're all blurry.
Yeah, they do all blur together, and because I haven't had an assignment every week, which I'm sure you guys are very sad about, I sort of track the passage of time in the term by how many assignments have gone by, and well, it's harder to do this term because it's so flexible.
I think it's week 6.
It can't be week 6. Is it really?
Week 7.
Drop day hasn't passed yet. Is that week 6?
It is week 7. No, I was my notes are like week 7.3 right now, so it's definitely.
Okay. Well, whatever week it is, it's definitely not week 2. So anyway, but we're going to spend basically the remainder of the class talking about transaction processing. That's how complicated a topic it is, but hopefully you'll start to appreciate how awesome it is as well, because I don't know very many pieces of software that really try to achieve this level of reliability or robustness or have quite the challenges to solve that database systems do in concurrent usage scenarios. So we're going to be going through a lot of that. Some of it will be reviewed from 121 if you happen to recall that stuff. But what we'll do today is start to develop the basic needs that we have of database systems if we're going to implement this whole concept of transaction processing and what those needs are and so forth. So we'll start developing that kind of thing. Like I say here, we have a pretty sophisticated database now. In fact, when I was looking at NanoDB, I have a solution version that the TAs look at so that they can see how things should be implemented, and I usually give them code before office hours, but not always. And but it can do quite a bit by now. We can optimize join orderings, we can do grouping and aggregation. After next assignment, we should be able to do some basic index optimization. So it's pretty neat that we can do all of this stuff. And I've shown you how, but we haven't dove into implementing it ourselves, how to do things like query decorrelation and all of this kind of stuff. So we have a pretty sophisticated set of tools so far. But we still suck, because there's certain things that we can't do that really you'd like databases that are managing your data to be able to do. First one is that the database isn't reliable. So you do something and then the system crashes, you're running it on Windows for some crazy reason or some other, insert operating system that you hate into that statement. And so we have issues that I may lose data. Or I have a situation where I have a logical failure, like I have here on the slide. So it's not just that the system may fail. It may also be that I have a series of operations that I do, and then I realize partway through I really need to undo them. And I don't have a way of doing that so far. The other thing is that we have no way of handling concurrent access. If I'm using my database and I think, you know what, it would be really neat if I made this website with like all my friends could get on it and they could send messages to each other and post pictures of their cats and things like that. Well, I can't really use the database very effectively for that because I can't do concurrent access. So these are the two major issues that we still have that we need to resolve. And you can see by how much time is left in the term that these are pretty challenging concepts to solve. So the solution to both of these things is transaction processing, and so we'll spend a lot of time talking about what transactions characteristics are and how to implement these various characteristics. But transactions are very simple. It's just a series of operations that should be treated as a single unit of work, a single logical unit of work. And so we'd like, for example, all of the effects of a transaction to become evident to other people at once. Probably we'd like that. I mean, sometimes you don't mind if people see things partway through, but in general we'd like everything to become visible to other people at once. We also would like it to be that when a transaction finishes, that its effects stick around. And so you can think about, okay, well, what are these kinds of characteristics that I'd like to be able to have? So clients do have to tell the database when a transaction begins or ends. It's kind of like memory management. The system doesn't know when you're done with a piece of memory unless it has a garbage collector or something like that. So, if you're in C or C++, you have to tell the system that you're done with that piece of memory. Same thing with transactions. You tell the system that you want to start a transaction, and you'll notice that there's a lot of different ways people can say that. So The standard way is to say start transaction, but you can also say begin transaction or begin work on many databases. I don't remember all the ways that you can say it on NanoDB, but you could look at the parser. It'll be in the assignment that talks about it. And then you can also complete a transaction. So you can say commit, commit work, commit transaction, end transaction. There's a whole bunch of different ways of saying it. And what you're saying is, this is the point where all of that stuff that I did, I want it to stick around. And or I want it to become visible to other people. So like it says here, transactions generally should be indivisible, where if something bad goes on some way down through the transaction, we'd like to be able to undo all of the operations of the transaction. It's supposed to be an indivisible logical unit of work. Also, you may have a situation where, like I said, you realize partway through that you have problems, so you'd like the client to be able to abort a transaction or roll back the transaction. So there's various ways that we do that. You can say rollback or rollback work, and again, various database implementations have other ways of saying this as well. They almost always support a lot of different ways, just because it's easy to add that to the parser. You may also have an interesting situation where the database itself decides that you're doing it wrong, and it says you quit. Your transaction has been aborted because something went bad along the way, and so even though the client may still want to do more, the client can't, because the database will tell the client, I'm sorry, but your transaction was aborted through, causes maybe beyond your control. You can even have those situations as well. We'll talk about why you would have that when we start talking about concurrency control. But you can imagine something where maybe a series of steps in the transaction violates a constraint in the database. So the database says, I'm sorry, this transaction needs to be aborted, or there can be other reasons as well. There was something else that I wanted to say about, I don't know if any of you have used Postgres very much. But one of the interesting things about Postgres is that it's actually far stricter about transaction state than MySQL is. And so if you are doing something in a transaction and then partway through the database says, I'm sorry, we can't go on, then every time you issue a command, it's going to come back and say, I'm sorry, the transaction's been aborted. Stop telling me to do stuff. And then you have to manually acknowledge it by issuing a rollback or abort operation, so that the client, acknowledges that the transaction is aborted. So it's interesting. Postgres has this interesting thing, and that's why I would love to switch 121 over to Postgres, because then you guys could actually see that and get some experience with a database that's a little bit more serious than MySQL. Okay, ACID properties. So these are the fundamental set of transaction processing properties that we would like transaction processing systems to satisfy. Does anybody remember what they stand for? Without looking it up on Wikipedia. Yeah.
I remember a couple of them. I know the A is adversary, B is verb,
I is isolation. C is candy. No, it's not candy. It's consistency. So yeah, it would be good to memorize these things if you decide to go interview at a database company, because they will probably like it if you know what these things are. The ACID properties were devised by this really brilliant guy named Jim Gray, who is basically the reason why you can go up to an ATM and withdraw money and the bank won't lose track of how much money you have, or you can make phone calls on your cell phone and the phone company can keep track of how many minutes you have left and all of these kinds of things. Because he was really fascinated by transaction processing systems, and he figured out all of these essential characteristics. And so he won a Turing Award for it, rightly so. And unfortunately, he was lost in a boating accident. They never found him. And then, of course, 7 years later, they said, well, we have to presume he's dead. And sadly, all of this has happened in the last decade. So one day I had to walk into database class and say, Jim Gray is lost. I think he was going out on a boat to dump his mother's ashes somewhere and just disappeared. Never. And so they're wondering if piracy was involved, like real piracy. No. I think it might have been off Catalina Island or some island off the California coast. Because Jim Gray worked for Microsoft Research, and I think he was in the Bay Area. His office was in the Bay Area, but I don't remember exactly. So you can look up on the internet. But yeah, they actually mounted a huge search effort using Amazon Mechanical Turk and satellite imagery and all this kind of stuff. But anyway, sad story, but Jim Gray, brilliant guy. Yeah, he'll probably emerge somewhere as like the transactionator or something like that. So, yeah. I'm sorry? Yeah, he will cast down the forces of NoSQL. So here's the four ACID properties. So you have atomicity, which is that either all the operations are reflected in the database or none of them are. Now, obviously, from the standpoint of the transaction itself, it will see its intermediate state. But other people should see either all of the changes of the transaction or none of them. Then you have consistency, which, like it says here, execution of the transaction in isolation from any other transactions preserves all database constraints. So if you imagine that you were running a transaction against a database and you were the only transaction running, then the database should be in a consistent state before, and it should be in a consistent state afterward. And if the transaction does anything naughty, it's rolled back. So consistency is more important than transactions completing, which I think everybody sees is reasonable. So yeah, database starts in consistent state, and then the completed transaction also leaves the database in a consistent state. Isolation. This is a really fun one. When you have multiple transactions executing concurrently against the database, then they have to appear as if they're executing in isolation of each other. So they're not allowed to see each other's values and cause all kinds of spurious phenomena. We'll go through that in a lot of detail. It's funny because we're going to spend, I can't remember exactly the sequence, but I think we spent about a week talking about how to achieve atomicity and durability. And then the rest of the time we spend talking about isolation, because isolation is there's some interesting and challenging ways of achieving it. So every pair of transactions, T sub I and T sub J, get used to this notation because you'll see it a lot. It appears that either Ti completes before Tj or Tj completes before Ti starts. So it should look as if that's that there's some sequence that is sequential for the transaction to have been applied. They don't overlap in what they do. And then finally, durability. Another favorite of mine is that when the database says that the transaction has committed, it comes back and says, yes, I have committed your work. Then those changes are persistent, even in the face of system failures and meteor strikes. Now, obviously, that's going to be a little bit difficult to achieve, but you can achieve some level of durability, which is pretty awesome. Okay, account transfer. So yeah, this is the most common example. So I hate to use it because it is also kind of boring, but it's very easy to clearly illustrate the issues that you have with transaction processing. So transferring money from one bank account to another. And we have all of these SQL statements we issue. Select, maybe we do select for update. We won't talk about that right now. We do inserts or deletes or so forth. And so we'll just model these as reads and writes to various data values. That's really all we care about at this level. So transferring $50 from account A to account B. And this would be a transaction schedule. It's basically just saying what are the sequence of operations that the transaction wants to perform. And we really even don't care about the A becomes A minus 50 and B becomes B plus 50, except insofar as how it affects isolation. We really only care about the reads and the writes. But for now, we'll talk about this is what this transaction might do. Read A, subtract 50 from it, write it back. Read B, add 50 to it, and write it back. So he says here, if the database was in a consistent state before it, it should be in a consistent state afterward. And we may even have constraints that are not able to be enforced by the database itself. You can probably think of some examples. What would be an obvious constraint here about a balance transfer? A good consistency constraint. Can we say anything about, Yeah, the sum of A and B should be the same before and afterward. We don't create money. We don't destroy money. Destroying money would be bad for our customers and therefore our business, and creating money would be bad for us and therefore our business. So we don't want to do either one. So yeah, the sum of account balances should be unchanged by the transaction. Now, you may have other ones as well, like account balances shouldn't go negative, or that account balances can't be null. And some of those you could actually enforce with the database. You could easily put a not null constraint on balance, and you could put a check constraint on the account balance as well if you would like. Certainly possible to do that. But there's other things that the application that are important for the application to be correct that the database can't necessarily perform. And so those are the kinds of situations where maybe you roll back, or maybe you just design it correctly, and through testing you try to verify your design actually works correctly. So first scenario. Yeah, so a failure occurs after the first write, but before the second write. So we have a situation where the transaction is interrupted. So as far as atomicity is concerned, we have to make sure that all of those operations either complete or none of them do. So if we're given that the system fails between the first write and the second write, we have to have some way of undoing the first write. Which again is a very interesting proposition, because what you're saying is your piece of software completes a write to a certain data value, and then the piece of software crashes. And so at restart, somehow we have to figure out, oh yeah, T sub I didn't finish, and we changed A, and we now have to unchange A. So it's an interesting design issue. Yes? Is write equivalent to commit? No, it is not. Commit is a separate operation. Well, if we only have one copy of A, and we change it, then it'll be visible after the database restarts. So this, we'll start getting into how we might implement commits by the end of the lecture. It's really interesting that you can actually implement things like atomicity relatively easily. So yeah, if atomicity is violated, well, in this case, if you subtract $50 from A and write it back, and then don't get to write B, then you lost $50, and your customer will be unhappy. So that's pretty obvious. So yeah, we say that the database is in an inconsistent state in this situation. So let's say that we have another scenario where both operations complete, and then the system crashes. So now we wrote A and we wrote B, but then the system dies in some way. So durability says, what I'm saying here is that TI complete. So we're saying that the client issued a commit, and the database came back and said, yes, I have committed your work. All of those changes are going to be here. And then the system crashes. When it restarts, that better be there. That's what I'm saying here. If the transaction is durable, the database will still reflect the changes after the crash and recovery from crashing. And the client doesn't have to repeat this operation. Because you can think of a commit as being a guarantee from the database. Yes, everything you did is in there now. And so when you get that commit back, it should mean something. That's a good transaction processing system will issue commits that are actually trustworthy and meaningful. This is basically what I just said. Okay, let's see. Yeah, so, and then when you talk about isolation, obviously, you need concurrent access. Atomicity kind of implies concurrent access, but it doesn't require it. You should basically just be able to say, yeah, I'd like to be able to roll back this transaction, have none of the operations reflected in the data anymore. So that's atomicity is still relevant without isolation or without concurrent access. Consistency is obviously important, and durability is obviously important, but isolation is the one that is really about concurrent access. So we have two account transfers. One is going from A to B, and the other one is going from A to C. And so the question is, think about the file manager and the buffer manager as performing these operations in sequence. So the file manager has to do a read A, and then it could do another read A, and then it could do a write A, and so forth, but it can only do one operation at a time. So at some level, you're going to have sequential operations being performed. Maybe it's at the disk level. Maybe the physical device is going to be performing these operations in sequence. Which means that these operations can be interleaved in any possible way. Any reasonable way we might have them interleaved. And so we have to be careful that we constrain the interleaving of these operations so that it appears that the transactions execute in isolation of each other. Okay? So that it looks like TI executed and finished and then TJ started, or TJ started and completed and then TI started. Okay? So that's what isolation really means. And this is a very strong definition of isolation There are weaker definitions that we will get into when we start talking about isolation in focus. So like I say here, we could have a database that actually follows this rule. It always only executes one transaction at a time. The problem is that this is prohibitively slow because you have a lot of situations where you're manipulating different data values. So there's no real need to have those transactions executing sequentially. Now in this situation, we clearly do have a situation where the two transactions need to be isolated from each other in some way, because they do work with the same data value, A, in this particular case. So we have this notion of a serial execution schedule. And again, when we talk about isolation, we will revisit this concept. But serial execution schedules are ones in which each transaction goes in sequence. So there is no overlap whatsoever between executing transactions. That's a serial execution schedule. Of course, since it is slow, we'd like to come up with some way that's a little bit more clever. Yeah, so this is what I was saying before. Why slow things down if we're working with different records? So there are many ways to interleave these operations, and databases, if they're clever enough, can interleave things so that it looks like they're executing in isolation of each other, but they may actually overlap. So here's an example. We do TI does its read and write of A, then TJ reads and writes A, then TI reads and writes B, and TJ reads and writes C. Will it appear, let's say that TI and TJ both commit. Don't think about rollbacks yet, because we really aren't diving into this topic in depth yet. But does it appear as if TI and TJ execute in isolation of each other? In what order? Which one looks like it comes first? Yeah, it looks like TI comes first, and then it looks like TJ comes second. Okay? Does it actually save time? Yes, it saves a ton of time. Well, basically, what it allows you to do, and this is a bad example because we have shared data values, and a really good execution schedule, because think about what would happen if, let's just, I'm going to take a little bit of time out to discuss this, but let's say that we do this. TI reads and writes A, then TJ reads and writes A, and then TI decides to abort. What problem do we now have? Yes, that is exactly correct. TJ read a dirty value. And so if TI aborted, what do we have to do to make sure that we... Yeah, we have to abort TJ. Does everybody see that? That is called a cascading abort. We don't like cascading aborts because you could create an arbitrary long sequence of transactions that depend on each other, where when the first one blows up, all of them blow up. And so databases prefer cascadeless execution schedules. Now, unfortunately, what that means is that if TI reads A, and then TJ wants to read A, you do not allow TJ to complete that read until TI commits or aborts. That generates a cascadeless schedule. We'll talk about this when we talk about isolation. But in that case, you get really no benefit performance-wise by interleaving these two specific transactions.
So when
you get benefits when they are not using the same data values at all. Because basically, remember that reads and writes are going to be a small part of the actual operations being performed. They're going to be reading, they're going to be manipulating values in memory.
But for example, TI instead of reading A and doing something A with B,
yeah.
Then therefore would
yeah, if TI were reading and writing D instead of A, that's a good example. Particularly if some of those values were in the buffer manager and didn't have to actually be loaded from the disk. Then we could do those things completely concurrently on different processors, and we would have a big performance benefit. Okay, does everybody got that? That was a worthwhile little detour because we will be revisiting it, and it's good to start to explore the complexities of these things so that you're ready for it. But anyway, here, this is an example of a schedule that we call serializable. And in fact, it's an example of something called a conflict serializable schedule, because you can look at conflicting instructions and reorder them so that you end up with a serial schedule. Okay? So this is an example of how the database could interleave things to execute so that it looks like they are in isolation of each other. Okay, yeah, so what if we had this instead? TI reads A, subtracts 50, and then TJ reads A and subtracts 30 and writes it back, and then TI writes A back. And then you have TI reads B, and then TJ does its read and modify and write on C, and then TI completes its operation. Is this okay? No. Why is it not okay? Well, let's say that it executes exactly in this order.
You can't separate them.
Sure, yeah, you can't separate them. So you're already starting to think about conflict equivalence, which is really cool. Like I said, we'll talk about this in the future. But there's if you were to describe this in a more simplistic way, the problem is TI reads A, and then TJ reads A as well without having gotten TI's changes. So that when TJ changes A, TI clobbers A, or I should say TI clobbers TJ's write to A, so it's not aware that TJ was actually manipulating the same value. Okay? So we actually have a lost update. This is called a lost update anomaly, because TJ's update is just disappears. Okay? Which means, guess what? We just created $30, and banks are not allowed to do that. Okay? So that's not good. So you can see that isolation is really key when you have multiple concurrent operations that actually can manipulate the same values. Okay? This is why I would love to have a 7th assignment where you guys get to do isolation, but we may not actually get to it. I have a lock manager. You could implement parts of the lock manager, but I haven't yet incorporated it into the rest of NanoDB. So we'll see if we get there or not. We probably won't. Okay? Let's see. So how we implement ACID. You can see that all of these things are very important. And like I was saying, atomicity, consistency, and durability are all very important, whether we have a single-user database or a multi-user database. So that's actually why we're going to talk about them first, because isolation turns out to be quite involved. So yeah, so this is basically the approach for the last portion of the course, is that we'll talk about atomicity, consistency, and durability first, and then we'll talk about isolation and how we incorporate the two together. Because you can see this is going to affect the buffer manager, and it's going to affect the file manager. So the storage manager has to think very carefully about transaction processing. Okay, any questions so far? All right. Now, transactions do go through a series of states. Obviously, when you perform your first operation against the database, and this is one of the things that is interesting to think about, every operation that you perform against a database that supports transactions, every operation you perform is actually done in a transaction, whether you do it or not. And so a lot of databases have modes where you can say, is auto-commit on or off? And a lot of times, auto-commit starts out as being on, so that a commit is implicitly issued after every operation. And if you say begin, well, then that implicitly turns auto-commit off, and you do operations, and they'll be part of that transaction you started until you actually say commit or rollback. Okay? So we have an active state. This is the state where you're saying, yeah, I might do more stuff. I don't know yet. I have to think about it, but expect more queries from me or operations, updates. When you do that last operation and you issue a commit, then the database enters a state where it is partially committed, which seems a little bit weird. But you can have databases that actually perform consistency checks and so forth in the partially committed state. Or it has all of the writes you did, but it hasn't done whatever that magic waving of the wand is that turns the transaction from active into committed. So you enter a partially committed state. What you're saying is the client's not allowed to do anything else, but the database might have to do stuff. And so that's what the partially committed state is for. So the database starts going about the operations that it has to perform. Maybe you have values that are in the buffer manager. And they aren't on the disk yet, so how is the database going to satisfy durability? How is it going to issue a guarantee when it says, yeah, I committed your work? So it may need to go through and push data out to the file system. It may need to verify constraints if you have deferred constraints that were deferred to the end of the transaction. So you have situations like that. If all of that works, then the database is happy, and it can turn around and say to the client, yes, your transaction is committed. So when we enter the committed state, we're saying this set of changes or operations is now durable, and I'm going to expose those things to other people as well. So like it says here, it goes to the committed state. Now if badness happens, it goes into a failed state. Now there's another way that we could go into the failed state where the client says rollback. Okay? And so you can go from active to failed as well if you say I want to roll back the transaction. Again, we may not be complete at this point because now you've said I'm not issuing any more operations. I've given up on this transaction. But there may be changes that need to be undone in the database. So it goes through that sequence of operations to go through and undo all of the things that the transaction may have done. And then finally it enters the aborted state, at which point the transaction's operations, its mutations that it may have performed against the database are all cleaned up, and it should be as if that transaction never occurred. Okay? Yes? Well, that's a very interesting question. We'll go through how this can be done. You have various ways that this could be implemented. Like the database may catch a constraint violation through throwing an exception. Like that's basically what NanoDB would do. I haven't incorporated that component back in. But one of the things, some of you may have noticed that there's this whole event processing mechanism in NanoDB where like you get before row updates and after row updates, and you can get before commands are issued and after commands are issued. And that's a perfect place where you can incorporate index changes. So like after a row's change, or I should say before a row's changed, you can look at the before and after values, update your indexes appropriately, and you can also do consistency checks in some of those places. So it's a pretty simple mechanism, and if something fails there, you could throw an exception. But there may be other ways that it's done as well, because not every database is implemented in a language that supports exceptions. Well, let's say that, for example, you try to do an update on a table that has a foreign key constraint to another table, and you update the table in such a way that that foreign key constraint is violated. That would be an example. The database detects that, and it says, okay, you were naughty, and it says the transaction is now entering the failed state, and it can either go straight into aborted after rolling back all the changes, or it can wait for the client to issue the rollback, like Postgres does. Okay? So, and if you're curious about how we actually implement this, we'll talk about that in a second. We'll start introducing ways of managing this series of transitions. Now, if we're talking about durable transactions, you can see that it's really important that we actually have some way of storing things that last through program failures, system failures, and so forth. So we need to start talking about storage media again. We talked about the storage hierarchy. And we have this distinction between volatile storage and non-volatile storage, where volatile storage does not survive through a system crash, okay, or more particularly a power loss. Because you can't have some that's, actually you can't have anything that satisfies or remains through a system crash unless you're really lucky. You generally don't depend on data being around through a system crash if it's in volatile storage. Secondary storage tends to be non-volatile. So I write it to a spinning magnetic disk, or I write it to a solid-state drive, or a tape. If you're stuck with tapes, then you could write it to a tape, and it would be non-volatile. Okay? And that is going to survive through power loss. Of course, you can still have other issues, which are important to consider. Data corruption. What if you have a situation where you are cursed with the prospect of trying to write out a sector and half the sector got written successfully? How do you detect that? Or if, like we have in our situation, disk pages span multiple sectors, what if sector writes are atomic, but page writes are not atomic? So you have part of the page was written and the rest was not. So you still need to deal with those situations. So yeah, storage characteristics, you can break them down by reliability, volatile storage, and non-volatile storage. There's another kind of reliable storage, which is our dream. This is like if everyone could have a pony, this would be exist as well. Stable storage, where it is never lost, never gets corrupt. This is very difficult to achieve, but people do the best that they can to achieve this while still being practical. Okay? It's like trying to build an airplane that can never suffer a mechanical failure. We do it the best that we can, but if we tried to achieve that ideal of it would last forever, then it would probably be too heavy to fly. So same thing with stable storage. Now we usually perform our transactions in volatile memory because otherwise it would be slow. It would be dumb to try to just read and write to the disk all the time. Our disk light would be on all the time and our database would be slow. So in order to make the transaction durable, we have to think about, well, if I have all of this state change in memory, I somehow have to get it out of memory, out of volatile storage, and down into non-volatile storage in a way that I can guarantee that it actually makes it. Okay, so like I say here, transaction durable, we have to make sure that all those effects are recorded in non-volatile storage to make it atomic. I need to have some way, this commit operation, which like I said is right now it's waving a wand, we have to have some way of having a single operation that we can perform atomically that changes all the changes we made, or that exposes all the changes that we made in one atomic step. That's a challenging thing to do. Yes? Flushing the cache, it will be probably more than just flushing the cache. Yeah. In fact, we'll talk about this because you can imagine if I'm flushing the cache, what if I touched 5 files? Is there an atomic way that operating systems provide to persist all the changes I made to 5 files to the file system in one atomic step? Yeah, so you write everything in the cache to disk, and as you're doing it, the system crashes. It has to be atomic at the operating system level. This is the challenge. This is the issue with committing stuff. We'll go through this in a little bit more detail. We'll develop this, and hopefully it'll become clear how we do this. So like I say here, to make a transaction durable, we have to make sure everything goes into non-volatile storage. The problem is not just our buffer manager. It's also the operating system's file system buffering. And it's the disk's buffering on the disk device. There's all these places where caching occurs. And we talk about this in CS24. We have all these layers. And we have to have it because the disk is like 1,000,000 times slower than the processor, or 10 million times slower than the processor. So we have to have all this buffering to make it fast. So what this means is the operating system has to have some specific operation that applications can rely on, where if you issue this operation, all of the data that may be buffered in all the various layers of the system can be guaranteed to now be on the disk. Anybody know what that operation's called? Like on Linux, on Unix? File sync. It's like fsync. If you do like man fsync, you should see, I think it's fsync. It could be sync as well if you're talking about the low-level system, but fsync is generally what it's called. And the idea is that if you issue an fsync, and fsync returns, then all the changes you've made to that file are actually on the platter. Okay? Not just in the disk's buffers, so forth, unless it's non-volatile memory, because you can't have disks that are cool that way. But that it's actually on the platter. And if you said fsync, and then you went to the wall and pulled the power out of the wall, plugged it back in, that data is still on the platter. That's the guarantee that fsync is supposed to provide. Yes? How is it different from writing the cache? Well, like I said, you write let's say that you purge your buffer manager out to, well, the operating system may still have it cached in its buffers. And so that's the thing, that's the frustrating thing about NanoDB, because there is like a flush all operation on the buffer manager. So you issue the flush all, that doesn't mean that the operating system has actually written it all out. And when the operating system writes it all out, it doesn't mean that the disk device, like the physical device, has memory buffers on it. And the operating system says, I want to write this out. And the disk is like, sure, I'll write it out. And it buffers it so that it can schedule the order of those operations. So you have no guarantee that the writes have actually pushed the data all the way down to the platter. The sync operation is the thing that actually makes that guarantee. Okay? Now there's other issues as well. You don't have any guarantee as to the order that those writes are going to occur. But we aren't going to talk about that right now. We'll talk about that when we get to isolation. To make a transaction atomic. So yeah, we have to record the transaction's effects to non-volatile storage in a way that all effects become committed at once. Now there's other operations that need to be atomic if this is going to work. And like I say here, the operation either completes successfully or it doesn't complete at all. There's no way to have a partial failure. And again, if you look at Unix file I/O operations, you'll notice that there's certain things where it says, this is atomic. Renaming a file is atomic. So for example, I have an old version of a file and I have a new version of a file. And I want to rename the new version to be where the old file was. That's a rename. And Unix guarantees that rename will be atomic. Okay? Unlink is another example. When I perform an unlink, if unlink returns, it's atomic. It happens in one step. So like I say here, it's also atomic in context of concurrent usage. Now let's start talking about hardware failures. That is another thing that can actually interrupt some of these operations. And you see some really interesting, and I would say, if you're talking in Wikipedia parlance, you'd probably put like citation needed next to the claim. But one of the claims, for example, is that when you try to perform a disk write to a particular sector, the disk will always be able to complete the write to the sector. It'd be really nice if you could actually guarantee that. So like it says here, during an fsync or a write operation, power fails. You have to be able to design, if you're writing a good database, you need to be able to deal with these issues as well. You have to be able to identify corruption occurring even in these operations that are purportedly atomic. There are some strategies you can use. Let's say that you're trying to write out disk pages. Can anybody think of a way of detecting if you had a failure partway through writing a disk page to the platter? There's a pretty easy way. I would expect somebody to come up with it. Are people familiar with checksums? So what you could do is say, well, every disk page has a checksum. And I will always store a checksum with the page data. And when I load the page data, I will compute the checksum of the contents of the page. And if the stored checksum and the page's checksum don't match, then I know that there was corruption. So that would be one way of doing it. There actually turns out to be a simpler way, which I love. And so I totally want to share it with you all. Again, Jim Gray talks about it in a book that is titled Transaction Processing. It's a very simple approach. What you do is you have a part at the first byte of the page or the first word of the page, and another part at the last word of the page. And you either write all zeros or all ones to those two values. So either all 0 bits or all 1 bits. And every time you write to the page, you toggle based on what the old value was. And so when you load the page, if you see zeros at one end and ones at the other end, you know you had a failure. Or vice versa. You have ones at one end and zeros at the other end. You have a failure. Much faster than computing checksums. I love it. It's really cool. Is it a most commonly used method? No. For example, Postgres does checksums. And so there's definitely places where checksums are used. If I were going to implement a system that required that level of durability, I would use this bit flipping technique. Because it actually is pretty dang good. Okay? So interesting thing. Okay? So there's things like that to consider. Let's see, yeah. So basically what we're talking about here, though, is that the database server is limited to what the hardware's guarantees really are. So if you're running on a RAID file system with redundant disks and the RAID controller has non-volatile memory on it, great idea. So that, again, the OS performs a write, the RAID controller caches the data in non-volatile memory so that if the system dies, we're okay. And a lot of RAID controllers, like really good ones, can perform journaling. So you have all of these things, and you have a file system that has journaling. You can get pretty dang good. You can get really close to this whole stable storage thing. Now, if you have Godzilla come out of the ocean and destroy your server farm, well, then that may be something that prevents stable storage from being achieved. So you have to think about all of these kinds of things if you're designing a data center. I'm not going to spend too much time talking about it. Now, the big issue that we have is that our tables do exist in multiple files. And when we have this fsync operation, it's only for a single file. And so for writing to multiple files that are different parts of the same transaction, we have to think about how do we actually get all of those changes to become visible in one shot. So like I say, there isn't a way of updating or modifying multiple files in a single atomic operation. So here's an example thing that we could try doing for commit. We write each dirty page to disk, and so we say for files 1 through n that we modified, for pages 1 through m that were in each file, we write each one of those pages out. So now we know the buffer manager has no has no dirty pages in memory. And then we fsync each file. The problem is if we have a crash during that sequence of steps, we haven't preserved durability or atomicity. We have lost some of our changes because they may be in some buffer when the system went down. So you can see that the tools that we have so far, we can't use them in this way to achieve a durable and atomic commit. Does everybody see that? So what we need to do is we need to find some way to take this sequence of steps and turn it into a sequence where one operation, we go in one step from not committed to committed. That's the challenge. We have to do it since we have these tools that the operating system provides, but they involve one file. Then we need to figure out how can we go from uncommitted to committed. Yes? Very good. You guys all hear that? Let's say we make a copy of a file. So we'll actually talk about using that approach. But what we're going to do is require, I hope you didn't look at the slides earlier.
No.
Because that's actually, yeah.
One step, that's just changing a point.
That's exactly what we need to do. We need to come up with a way to make a bunch of changes that it's okay if it fails during that series of changes, but we have one change that's sort of like flipping one of these awesome old school knife switches from uncommitted to committed. So we have a system now. We're going to require only one transaction at a time. We can have multiple files. When somebody wants to make changes, we make a copy of the database, the entire thing, all the indexes, anything else we decide to save. And we start performing our writes against the copy, not the original. So we have somewhere a pointer to which version of the database is the current version. Okay? And so you have this DB pointer. Maybe it's in a file all by itself. And a DB pointer certainly would require only one sector. So we can hopefully write sectors atomically. It seems like we could probably change the DB pointer atomically. So maybe that'll be our commit. So we perform our reads and writes against this copy. And so here's what we do at commit. We write all the dirty pages to disk. We do that series of steps that we had before. For each file, we iterate through the dirty pages in that file and write each one out. And then we sync each file. So we know that the data is on the disk. Then we can perform our atomic commit operation. We change the DB pointer in memory to point to the new copy, which better be consistent if our database doesn't suck. And then we write and fsync that value. And at the point that we fsync, we can guarantee that the transaction is committed. Okay? Think about what would happen if we write it and we didn't fsync and the system crashes. Well, if the write didn't hit the platter yet, nobody cares. We have the old version. If the write did hit the platter and we didn't quite get around to fsync, well, it should have been an atomic write. So if the system crashes and it comes back, we'll see the new version. If the fsync is issued, and you could apply that even if the fsync is issued and crashes before fsync returns. But let's say that fsync returns. Well, then we know that the new version is going to be in flight. So it's nice. We have a way of either having the old version or the new version. And we can do it all in an atomic step. Now we have cleanup, of course. We'd like to delete the old version, but if we have a crash after the fsync, but before we delete the old version, that's no big deal. The transaction is still durable and atomic. Any questions? Why don't all databases work this way? For some obvious reasons, right? It's very slow. Yeah, so aborted, so we just delete the new copy of the database. And the DB pointer still points to the old version, so we're perfectly fine. Is there a question, comment?
Yeah, so why do you need to create a copy of our database? Or can you keep like some sort of log where you just write what you did or what changed?
Well, that's a good observation. Like, why don't we just keep a log? That's in fact what database systems do. But what we're doing here is we're prizing out the essential requirement for providing a system that can do transaction processing and has a meaningful commit or abort operation. Because the write-ahead log becomes that thing that we fsync on, and once we fsynced on it, that becomes a commit. But even that's not good enough because transaction logs can get large, and so you'd like to roll over to another log. So then you have to write all the logs, and then you have some other file that's very similar to a DB pointer. It's called a checkpoint record. And the checkpoint thing is what's fsynced, and that becomes your commit. So we have various ways that we can do this. But yeah, we'll get into a much more optimal way of doing this. Start hopefully next lecture. Yes. It's starting to sound a lot like Git. Well, good, because Git doesn't suck, as far as transaction processing. Back in the world that I emerged from, where we had this version control system called CVS, you could have non-atomic commits. You could check out while somebody else was still in the middle of a commit. Subversion was supposed to fix that, so it got better. And then Git got even better. Okay? But yeah, so you have these kinds of things. We'll talk about this more in the future. So really quickly, shadow copies. Yeah, we're going to go a little bit over time. But you guys have been making some really good observations. So yeah, this is called shadow copies. And the one obvious issue is that we have a lot of I.O. being performed. You can improve that by doing shadow paging, which is what your operating system actually does with virtual memory. But the real issue here is that you can't have overlapping transactions. That's the real issue with this approach. You can't have concurrent transactions. So this situation is used in some circumstances, or this approach is used, shadow paging, when you can actually guarantee that you only need to do this one transaction at a time. But it's not used very widely, obviously. Okay, so the last thing that we'll talk about, it captures this essential requirement. And this is really the punchline that I want you all to get. We have to figure out, if we're building a transaction processing with the atomicity and durability, we have to have that one operation that changes things from being uncommitted to committed. And you can pretty much design that into any system. Like I said, you have write-ahead logs. Well, that sounds good, except that you need to roll them over and create multiple logs. And if you have a transaction spanning multiple logs, now you have two things that you have to sync. Well, introduce something that makes it one thing, and that's a checkpoint record. Okay? So I think you guys have gotten it. So we make all the changes into a copy of the database. A final commit operation is just that one change. And so yeah, like it says here, if the system crashes, then in recovery, the database can just abort by deleting the new version. Okay? And so you will see this fundamental approach in all of our transaction processing discussion. We have to have one thing that we do that changes it from being not committed to committed. And so if you ever find yourself designing a transaction processing system, that's the pattern that you have to get to. Find a way to make all of your changes in a way that doesn't affect everybody else, and then have that one thing that you do that changes it to make it visible. And that actually is an underlying characteristic of read, copy, update, which is very cool, but take the OS class if you want to learn about that. Okay, any questions? All right, we'll pick this up on Monday. We'll develop